The first experiments within the fundamental research program at the NICA complex will be conducted using heavy ions. Therefore, I'm going to tell you about the heavy ion injection chain of the nucleotron first. The heavy ion injection chain is intended to inject heavy ion beams, up to gold ions, of fully stripped nuclei. Therefore, the energy of these ions must be sufficient for the effective stripping of the electrons, which remain in the source. That corresponds to about 600 megaelectron volts per nucleon. The injection chain itself consists of the following main elements: a heavy ion source, two accelerators, such as a linear accelerator and a small-sized synchrotron, also called a booster, and a few transport lines. A beam transport line of low energy runs from the source up to the entrance to the linear accelerator. Between the sections of the linear accelerator, there is a beam transport line of medium energy. Further, from the linear accelerator, a beam is transported into the booster, followed by the beam transport line from the booster into the nucleotron. An ion source based on the electron beam is used in the heavy ion injection chain of the nucleotron. This source is called an Electron Beam Ion Source in English, and it was invented at our institute. An author's certificate was issued in 1967 to Evgeny Donets. Since then, this type of source has been under development not only in our country, but also abroad. Notably, sources of the same type are used in the heavy ion injection chain of the relativistic heavy ion collider for obtaining the same gold ions. What is an electron beam source? Commonly, ions are obtained from a substance in a gaseous state resulting from ionization by an electron impact. An electron beam source has an independent system of electron beam formation, which actually performs the ionization, and a system of puffing the required gas into the independent system of electron beam formation. Whether it is ion evaporation of gold or other metals from a solid state, or puffing the gas, if ion acceleration of noble gases is assumed, such as argon, krypton, or neon. An electron beam is generated by an electron gun. Then it is transported through a relatively long rectilinear section into a superconducting solenoid field. After exiting the solenoid field, it ends up in the collider. There are electrode systems, or so-called drift tubes, located along the direction of movement of the beam. These are hollow cylinders with various potentials applied to them. Inside an electron beam, there are atoms of the same substances, the ions of which need to be obtained. To lock ions inside an electron beam, certain potentials are exerted on the drift tubes, preventing the ions from withdrawing along the electron beam. The electric field of the electron beam itself prevents these ions from withdrawing across the electron beam. Thus, a potential ion pit is created for the ions, emerging from residual gas atoms. Due to the ionization by electron impact, the charge state gradually increases. The maximum current of such a source is determined by the electron beam current. When inside the electron beam, an ion charge is accumulated, which is exactly equal to the electron beam charge, and as a result, nothing withholds the ions transversely, and they start leaving this trap. The charge state of the ions, generated in such a source, is determined by the energy of the electrons, meaning by the same binding energy which may remove the electrons from the ion, and by the ionization time. Ionization takes place consistently, and depending on the ionization time, various charge states may be obtained, whereas the maximum possible charge state is determined by the electron energy. Besides that, the maximum gained current in an array of operation modes also depends on the value of the magnetic field. Why was this exact kind of source selected for the injection chain of the Nika complex? First and foremost, in this source, after ion accumulation in the trap, potentials on the confining electrodes along the beam can be changed, and an ion beam may be extracted. The extraction duration is very well regulated, and hence, an equal duration of the revolution period may be chosen in the cyclic accelerator during the injection process. The periodicity of the ion current from an impulse to another impulse is very good, and a sufficiently high charge state may be obtained. Such a source is almost ideal for use with the following synchrotron, where it is possible to match the ion beam parameters from the source with the requirements of the subsequent cyclic accelerator. In addition, this source is easy to control and has a long lifespan, meaning there is no element in it that needs regular replacement. In the 90s, this idea was developed at our institute, and the operation of the electron beam source in the so-called electron reflection mode was proposed. For example, in the basic scheme of an electron beam source, a potential that is equal to the potential of a cathode may be applied on a collector of electrons. Meanwhile, after one flight inside the source, electrons will get reflected against the collector and will start moving back to the cathode. They will get reflected again against the cathode and will generate many oscillations in such a system. With a certain ratio between the source parameters, from such circulating electrons, a new phase state of the electron beam is created, which has been called an electron string. The effect of the electron string formation was discovered in the early 90s. Later on, it was tested on a number of sources of this type. The first specialized source of an electron string type was created at our lab. Known as Cryon 2, it is operated on the basis of a solenoid with a magnetic field value of up to 3 Tesla. In such a source, the accumulated ion current is proportional to the magnetic field value, and a further increase in intensity is attributed to an increase in the magnetic field value. One of the positive distinctions of this type of source, in comparison to other heavy ion sources in a high charge state, is a relatively narrow ion spectrum. For example, this picture shows the spectrum of argon ions, obtained on an electron string source after 500 milliseconds of argon atom ionization. The result is almost ideal. In one charge state, the argon-16 beam. The required charge state may be achieved by varying the ion beam confinement time in the electron beam. By extracting beams, sooner or later one may gain a lower or higher charge state. Generally, as far as a charge state is concerned, this source generates approximately 20% of target charge and up to 20% of neighboring charge states. For the Nika project, a specialized electron string source with a magnetic field of 6 Tesla has been under development in order to raise the beam intensity. We expect the energy of the electrons to be anything up to the amount of 25 kilo-electron volts, which makes it possible on this source, besides the required gold ions in the charge state of 31, to raise the charge state to about plus 59, which might be interesting in some modes. But actually, its crucial task is to generate 2.5 times 10 to the power of 9 gold ions in the charge state of plus 31 at a sufficiently high impulse repetition frequency to effectively use the booster. The impulse duration of the booster injection is about 8 microseconds. Respectively, the ion extraction time from such a source is approximately 8 microseconds.